Hello and welcome. The purpose of this video is to cover lesson 3.5a dealing with functions and specifically how to know when a relation is a function. So I'm on page 161, sorry about that, page 161 of your textbook, lesson 3-5 functions, and we are specifically interested in this first idea here. Know how to identify when a relation is a function. So your book spends a little bit of time talking about relations and functions, introduces you to some ideas of some notation, which you'll see here. F of x is equal to mx plus b, for instance. What we're going to be interested in eventually, not in this video, but eventually, is we're going to be very interested in learning what this f of x means. But we're not quite there yet, so we're not going to worry about it too quickly. As we scroll down the page here a little bit, before we get to the section 3.5a lecture, we see a definition, and there's some words underlined here: function, domain, range. The book gives you a really quick definition for these words and kind of ignores some other words which are also important. So before we get in too deeply, I'm going to jump over here and try to make sure that you've got the proper vocabulary for talking about functions. Now, before we can really define what a function is, we need to talk about a relation first. And I've defined a relation here as a correspondence between two sets of information. Right? You guys are used to relations. There are all sorts of things that are related one to the next. You are related to people in your family. There is an age that's related to you. There's a social security number that's related to you. The car you drive is related to its maker. There are lots and lots and lots of different relations, infinitely many probably relations out in the world around us. Now in math, we're mostly talking about relations between numbers, but they don't have to be, and you'll see some examples in your book that aren't. But let's see what we mean by this idea of a correspondence between two sets of information. The two sets of information are called domain and range, and our correspondence is always taking things from the domain and relating them to things in the range. So there's a direction here from left to right, from domain to range. And as a matter of fact, we often refer to this as a map. Right? We're taking things and mapping from one location or one value to another, going from the domain and the range. And our map can be pretty much anything with a relation once we have our two sets of information. So for instance, I could say that 1 corresponds to, relates to, maps to, we can use any of these words as synonyms, to 5. We could say that 2 is related to 9. We could say that -1 maps to 0. We could say that 4 corresponds to -1, 7 to -12. And some of these numbers might correspond, relate, or map to other numbers as well. So maybe 4 is also related to 16 somehow. And maybe 7 is also related to 0 somehow. So there's lots of different possibilities here. Matter of fact, we could have a relation where every single value in the domain is related to every single value in the range. May not be a very useful one, but we could have one like that. We could also have much more simple ones, for instance, where each thing in the domain relates or maps to the same thing in the range. Maybe everything maps to 0 for some reason, and we ignore all the rest of those numbers in the range. That's possible. Just about anything's possible, right? So that's what we need to understand first, is what is a relation? Because as we're going to see shortly, functions are special kinds of relations. Now before we get to functions, let's talk a little bit more about the idea of domain and range. And here at the bottom of the screen, I've written down some synonyms for domain and range. The domain we can think of as the input, because it's the place where we start. We also can think of it as the independent variable. That's a nice math term for it. For a lot of what we do, the domain is also x. The range is therefore the output. We take inputs to outputs, domains to ranges. Independent variables relate to dependent variables. That is, the value of a dependent variable is dependent upon the value of the independent variable. Or x's go to y's, and we saw quite a bit of that in section 2, where if we knew an x value, we could figure out what y value was related to it or associated with it. All right. As you'll see in a later video, y is sometimes written f of x when we have a function. So this is not true for relations in general, but it is true when we have functions. And we'll talk more about that later. All right, so what makes a relation a function? So a function is a relation where each input corresponds to only one output. All right, so let's draw a relation here. Let's say that B is related to A. Let's say that C is related to E. D is related to I. F is related to O. G is related to U. Let's say that H is related to E. And J is related to U. This is definitely a relation. Pretty much anything where we draw arrows from the left-hand side to the right-hand side is automatic relation. Our goal is to try to figure out whether we have a function or not. So in this case, we absolutely do have a function because B is related to only one thing, A. C is related to only one thing, E. D is related to only one thing, I. F relates only to one thing, G only to one thing, H only to one thing, and J only to one thing. So since each item in the domain, or input, is corresponding to exactly or only one output, then we have a function. So this is an example of a function. Notice that some of the range values are used more than once, and we don't care. All we care about is how many times the domain values are used. In this case, each domain value is used exactly once. All right, let me erase these arrows, and let's draw something that's not a function, but still a relation. All right, so let's say that we have something where B is related to A, but B is also related to I. Now we have B, one input, being related to two different outputs. That's not a function. All right, and that's all you need is just one. Everything else might be fine. Maybe C relates to E, and D relates to I, and F to O, and G to U, and H to U, and J to U. Everything except B is related to exactly one output. Those all look great, but because B is related to two, that is more than one item in the range, this is not a function, and that's all it takes. If you can find one thing that breaks that definition, one input that corresponds to more than one output, then you do not have a function. You still have a relation, but it is not a function. All right. Now let's jump back to the textbook and take a look at the examples that you have there. All right, bottom of page 161. Example 1, let me highlight it here. Example 1 says, would a juicing machine be considered a function, and why or why not? And if so, what would the domain and the range consist of? And the solution says that yes, a juice machine could be considered a function. The fruits and vegetables would be the domain, the juice is the range, and you expect when you put a fruit or vegetable in to get a very specific type of juice back out. For their example is if you put an apple in, you expect to get apple juice back out. Not banana juice, not grape juice. So an apple would go to apple juice, a carrot would go to carrot juice. One input would lead us to one output. We never have to guess at what might be coming out of our juice machine. We don't have to worry about multiple different kinds of juices coming out of our juice machine, assuming we're only putting one type of fruit or vegetable in to begin with. All right, let's take a look at example 2. Given the following sets, A is equal to A, B, C, D, and B is equal to 1, 2, and you notice these sets have curly braces around them. That's going to be an important piece of notation. We'll talk more about that in the next video. We're given those two sets, and we're given a relation called F, that's the name of the relation, that's defined as A is related to 1, B is related to 2, C is related to 1, and D is related to 2. So what I've done is I've kind of taken that relation, in this case the sets A and B. A is going to be our domain since things from A are related to things from B. B is going to be our range. And what we can do now is draw some arrows here. So A is related to 1. B is related to 2. C is related to 1, and D is related to 2. And in each case, there's one arrow leaving each input from the domain. A is related to only one thing, B is related to only one thing, C to only one thing, and D is related to only one thing. Therefore, this is definitely a function. Right? Sometimes drawing these graphs can be a little bit easier than trying to puzzle through the way things are written in the actual problems themselves. All right, one more example we'll take a quick look at here. In example 3, and let me highlight that so we can find it. Oops. All right. We're given the following sets A, which includes A and B, so I've done that as my domain. I just put a capital D because I'm a little squished for space here. But the set A has A and B in it, that's our domain. B has the elements 1, 2, 3, and 4 in it, that's our range. So I've made the range 1, 2, 3, and 4. And we're given a relation F, which is defined as A relates to 1, B to 2, A to 3, and B to 4. We're asked if it's a function. So I'm going to draw A relates to 1. That looks good. B relates to 2. That looks good. But then all of a sudden, A relates to 3. Well, A is already related to 1, so now A is relating to something else. Now we have an input related to 2 outputs. This is a relation, but can't be a function. If we finish, B is related to 4, so we also have a problem there. So we have both of our inputs are related to 2 different outputs. So for example 3, this is not a function. And that's because at least one of the inputs has more than one output.